Hello everyone, my name is Tamira and this is my colleague Avishek. We're coming from TU Munich and we're working together on a DFG research project containing the information backbone for robotic construction, which integrates task planning and robotic simulation.
So our project is DFG funded. It's called FR5672, the code name, and then the title is Information Backbone for Robotic Construction. It's a collaboration between 4 universities, 2 chairs of Technical University of Munich, Digital Fabrication, and chair for
simulation for built environment.
Yeah, and then with Hamburg University of Technology, University of Duisburg, Essen, and TU Berlin. So our goal is to make robotic
ma ei tea otseselt midagi suurejoonelist vist ei olnud plaanis seal.
Including the logistics.
Yes, so we start with some introduction and motivation. We figured that there are several projects bringing robotic to real construction sites, containing, for example, the design to execution gap, how we really bring the design to the execution on site, how can we handle that, or also the interoperability between different robotic systems. There are ROS-controlled robots, there are robotic systems for bricklaying or for timber construction, but not together in one system yet. And there are also weak feedback loops most often, like how do we get it back to the design, all the way to the task planning. It's sometimes there, sometimes not, but not as in an overall system where the data is connected and interflowed and interchanged. So we define some required capabilities. We want to have traceable model task relationship, so each task is connected to a model element. With that, then we can have coordinated multi-robot workflows and runtime feedback and monitoring, as well as one common information data structure. For that, we came up with some concepts. We want to go from planning and design all the way to the robotic execution by introducing the BIM-FIM-RAM pipeline. So we called, it's like just some abbreviations. So we start with a building element, refine it into a fabrication information model, which is then essentially a brick, for example, and then refine it even further and add the robotic information, for example, the trajectory. How are we going to do that? We defined a system of microservices. So we start with a model interface service to upload the model and register all the agents on site. Then in the second step, we have a FIM generator, which generates the FIM out of the model, and a task manager, which then generates tasks based on the model elements, connected to a planner, which plans basically which task is coming in which order. All of that is then connected to an instruction and feedback manager, which handles the feedback coming back from site back into the tasks. Of course, the task can also directly receive feedback from the site, depending on which system you use. For now, we use behavior trees for that, not in the way they were originally planned, but more as an overall orchestrator for the tasks. So let's have a short look about our technical stack. On the top layer, you can see the application interfaces. We have a web UI, of course, with a 3D viewer. Then, for example, in a second layer, you can see multiple services. This is just a few of them. There are more, and they can also be, what is the nice thing about microservice, extended to any service you need or might need in the future, because for now we cannot see what we might need in the future because it's just at the beginning. So probably we have to extend that stack later. And we have a communication layer consisting of 3 main communication technologies. The REST APIs for the service handling, a Kafka event bus, similar to the MQTT you presented, for handling the communication to the robots or to the simulation, and some WebSocket services for the live feedback and state tracking. On the bottom layer, we also have some robotic stack, of course, and data models, as well as deployment infrastructure. So after the model is uploaded, we can generate the FIM, and what we are showing you today is the way from the web UI all the way to the execution service. which then sends out a task through Kafka event bus all the way to the Isaac sim simulation. And from there, Avishek generates some movements, and the movement is executed in a simulation by the robot. And Avishek is continuing here.
Yeah. So on my side, what I do is we have created another technical stack on my side, which is the product or the build structure that is handled by COMPAS and Rhino geometries, and then I convert them into OpenUSD to simulate in Isaac Sim and in other software interchange, and it's all handled through Python. And basically what the Isaac environment does is simulates the process of the building. So essentially what we do is we use the assembly information model in our chair, which is based on the COMPAS, like the core COMPAS. We translate that into OpenUSD through JSONs, and we add certain layers of physics like rigid body colliders, surface materials, and certain semantic schemas. The reason behind is that whatever data we have on the nodes, we translate that into custom properties and the semantic schema of the USD files. It just makes the cat file behave a little bit like real objects, and that's what helps us simulating using Tamira's interface. So essentially we take the abstract representation with the geometry, and we add basically a couple of other functionalities to expand the capabilities. So how do I play this? Yeah, so basically here we're showing like how we are importing geometries and the robots, and this is the simulation client, this is the IBRC interface, and then here Tamira sends the instructions, and then for this one we have only one command, that's a move to command we have integrated, that we can move our robots, and there are other tasks. So right now from the IBRC interface, we are sending the commands where the robot is executing certain tasks. We have to test that with using real robots, but for the safety, we are using the IBRC here and the Isaac in the simulation, and then it sends a feedback to the IBRC that I have completed the task. Sometimes the task does not go that well. Okay, it doesn't play, so it. Yeah, the access is restricted. I have no idea why, but it shows that sometimes it also crashes the geometry. So no. Yeah, I'll have to just do that.
The interesting thing about the system is that we don't say what the robot has to do, but we leave the autonomy to the robot how he fulfills the task. So it's a bit different. Like the backbone is more the central brain, but not knowing how the robot in the end moves to the object. So it's more like an overall framework, probably.
Yeah, so basically sometimes it does that,
Yeah.
and but it's not so nice all the time. So
Yeah.
that's why we're sticking to the simulated robots for a while now, until we figure out all the kinks. Yeah, that's us. Do you want to add anything?
No, I think it's fine. Thank you.